Hey, I'll record a video about how to optimize a little bit the code for the colors assignment. As this colors assignment is quite computationally heavy, so there is some problems when you are trying to run the simulation, or you might running the robot physically, then you will maybe encounter some performance issues, especially if you are doing this assignment where you have to look at the colors of the objects as well. So you this C2 and C3 already. So you need to find different color objects. Well, C2 is actually the most important task for this. So basically, I have created different implementations for potential optimizations. So I actually created some different bounding box implementations that we did already in X06, and we created a method called this get object bounding box list, and I took this method, only this one, not the method for angle calculation. So, and applied different optimization techniques to this method. So I create for reference, I included the original one. So this is this for loop flat fill algorithm that I also showed in the video. And then in the video also I said that if you want more performance, you should use SciPy label. And then I also implemented this and included this in this benchmarking application. So after that, I created an optimization using something that is called threading. Many of you might already have heard about this. I don't know if it is also in this previous courses in Taltech, but this allows using this parallel or different cores of your computer processor and run calculations in different threads in parallel, so it makes it faster. Then I created another optimization using something what's called the thread pool, and I'll discuss this maybe later. And then something called using region properties. This is a scikit method or function that you can use, but I'll maybe discuss this later. Then I use the same optimization, but when using a thread pool. Then I used optimization with number. So this number actually compiles the function that you decorate with this number decoration and compiles it into C code or very optimized code that is then executed instead of this Python code when you're running it. And then I created another optimization with number, but this time there is an option to parallelize actually this function call. So basically it kind of does it the same as in threading in some sense that it tries to find some ways to utilize different cores of the processor of your computer and optimize the performance. And there is actually an extra one for this bounding box here, which actually means that it is not necessary. I will just update this. I will update this with this one instead. For loop bounding box list number, and we will measure that as well. So then I created this sense with this set image calls. So basically in each of these implementations I created this extra method to give this image as an argument, or to pass this image into each of these implementations. And then we have this measurement here, and for each implementation. And then we have statistics part here. So we create an ordered dictionary, and we find the average times of each implementation, and then print this statistics out. So we will see how well it is performing all of these different implementations. So I had to do a little bit of tricks to support this import for the simulator, because otherwise usually without these tricks you have to include all of these different classes, or everything has to be in this robot.py, but it is possible to create it in a way that you can have different files, but this is not the topic right now. So let's try to run this benchmarking, and we are running it on the second task, okay, of the colors. So as you can see, it takes quite a long time to start, and this actually happens here, that it is compiling, and it actually tells us that this parallelization technique was not possible even, but I'll get to that a bit later. But anyway, it started for quite a long time. So this happens because this number is compiling the code just in time, as the name implies, this GIT. And once it compiles it, then the performance will be better or fast. You just have to accept it that it will start longer. So if it's okay for that particular case, then it's fine. So if a program is running for a long time, then it's fine if it takes some seconds to start. But if the program runs for a short time, then every time to compile it, it actually forms quite a big percentage of the execution time, and then it might not be worth it at all. So here we have also, I'll show this part. So one of the easiest optimizations actually, as we kind of have already done here, is over here, is that we might not do any calculations at some steps. So here we have a basic variable here called this step, and we just check that when we should actually do anything in this sense method. So here we have that every fifth time, basically, we do these steps here that we have, and every other time, so 4 times, we don't do anything. And so that means we have a much faster running, total faster running program. So that gives us a performance boost altogether. So first of all, when you are trying to improve the performance, then you should think whether it's possible to just not calculate everything all the time. So think when you have to actually do this calculation, maybe there is no need to calculate these bounding boxes every step. Maybe you can only calculate at very important points. So maybe when you're scanning, and maybe when when you're driving to the object, then you can calculate you can skip a few frames and then calculate, and it will be also much faster. And here we have then this printing of these results is also done or calculated also every 5 steps. So it's a bit different than just doing it every step. And here we have then already sorted this list, and as we can see, this SciPy label in conjunction with this threading thread is in the lead. So it takes about 0.02, so that's about 22 milliseconds, right, for calculating all of these 3 color detections. And as we can see that this original flat fill algorithm is quite a bit slower, so it's 40% slower currently. But as we kind of know from the flat fill that it's not much different or much slower when there are no objects in the frame. So it's fast over there, but now that we have detected some object, the difference is actually quite huge. So as we can see, this flood fill is now the slowest, and it is getting slower with every update. So we can see that's already 160% slower, and it is actually going slower every update and decreasing. So there is this other flood fill plus number optimization seems to be holding up much better. So we can see, well, we passed all of the three objects, and now we have a bit of better statistics. So we have done like one loop right about now, and we see that this threading method is still ahead as it was in the beginning, but we can see that these number optimizations actually are moving up. So this difference is actually shrinking, and over time this difference is actually going to shrink so much that this number optimization actually could overtake this threading, but not by much. So I have run it previously quite a long time, but so just this part is maybe interesting here. Just these things here, because one approach was actually running with different implementation than was written here, but this part is still relevant, and so we can see that after like 23,000 steps, the difference was 3.7% slower. So as we can see, it has been running now almost maybe 2 loops, I guess. So this threading part is still ahead, but this basic flood fill algorithm plus Numba, it's not that much slower, as you can see. Percentage wise it's 20%, okay, but if we look at just the times, it's like a 4 milliseconds difference, so basically no difference at all. And as we can see, all of these optimizations kind of converge to something. So you can use different ones, but there might be like a small differences, but generally speaking, one approach does not give like ultra high performance boost compared to others. Right now, of course, we are using only the CPU. So if there is a GPU available, some optimizations can include running part of the calculations on the graphics card, and then the speed up could be much faster, in some cases hundreds of times faster than running something on the PC or the CPU. So as we can see, it kind of stabilizes in some sense, and we can see that these threading seems to be quite performing quite well, but the basic algorithm that I showed also in the video, when you apply this Mamba optimizations there, it's very much kind of the same. We know that these two will improve over time, but as we saw when we started the program, we saw that a warning that said that this parallel version when optimizing is actually it was unable to optimize in this case. So this difference is, let's say, statistically just noisy or noise, and in reality they actually should be the same. So for this case, so yeah, and this region props approach seems to not give any big benefit compared to our other approaches, and just using the label alone is actually quite a bit slower. So if you are not doing this threading approach, it will be much slower. But if we compare this flat fill that I showed in the video and this just using the label, the difference is quite big, so like maybe 2 times actually difference here. Okay, so let's look at the code of the implementations. So I don't know which way we should go. Maybe start with this the original one. So this is the for loop bounding box list. So this one actually is what we also saw in the video. So this all of this find blobs was basically this flat fill algorithm, and this is here, and then we had this like process blobs, and this process blobs actually we see that we have 3 almost exactly the same blocks. So we are trying to find the different colors. So here we are trying to find yellow. Here we are looking for the red ones and blue ones. I have maybe simplified or removed some of the parts that actually are running in the simulator, just so that the X06 does not get completely revealed with this video. So I have removed some parts, basically just this how to calculate this bounding box coordinates basically. And also I have removed these threshold values so that you can discover them yourself, and also these how to find the yellow color. Yeah, so that was kind of part of the previous exercises. So yeah, So this was the original one as we saw, and we know that this is quite a bit slower. I'll just leave it running in the background while we are looking at the other ones. So as we saw, this is quite slow, and this is what we want to improve. So next one here is actually this same approach, but optimized with the number. So what is different actually is this part here. Oops. So this static method decorator plus this njit decorator, and here we also have this argument that it should be parallelized if possible. So what is this number? You can read about this from the documentation here, but basically there is this 5-minute guide to number, and this in this number guide is something that is quite interesting for us, is that number likes loops and number likes NumPy functions, and this maybe is not that important here, but when we look at our code, then we see that there are loops here, quite a bit of loops, and there are NumPy methods here also, but not exactly here. But we have these, well, a little bit here, but yeah, this is not maybe the biggest issue. But just adding these decorations, we can already improve our result quite a bit. So this one is here, so it's almost the best, like top 2 after with just this optimization. As we can see here also, this for loop bounding box list number, and just make sure that it is correct here. As we can see, it's all should be correct. Yeah, so basically let's look at the next one. So we have SciPy label bounding box list version, and this, as we can see, is also uses like these 3 blocks here, basically 1 block for each color, but what is different than when we look at the other one, the for loop one, is that we are using this label which is from the SciPy, and when we look at this one, so this was the this version here. This is just the label, so it's faster than the original one, like 2 times faster, but still quite a bit slower than the best performance ones. Okay, so that's basically it. So next one is SciPy label bounding box list, but with threading. So when we look at this one, it's the best one actually. This is the best at this point of time. It's the best performance one. And what is then the trick here is actually what we do is we create a list of these masks, and we also have a list of the colors. So we have two lists, then we zip these lists together to create these arguments tuple, and then what we do actually is create a list for the threads that will be executed or run, and then we do a loop where we go through all of this arguments list, and we get the mask and color from this list, and then we actually start creating these threads, and this thread needs a target. So this target is actually what will be executed by this thread when we start it. So we say that we want to execute this method when this thread is started, and we say also that we want to pass this mask and color as arguments to this method, and that's basically how you create this object of the threading object, and then we append it to the list of threads, and then after that we start the thread. So we start the thread, and it starts executing, but we actually go back and create a new thread. So we created one for the blue one, now we create one for the red one, and then we create one for the yellow one. But as we create them, we start them immediately, so they actually start running in parallel. So we are not actually blocked here, so it will continue running here. And after we have started all of the colors detections, or the bounding box detections, we go here and we then actually wait for all of the calculations to be complete, and this is done with this thread.join. So what happens is we stop here until this particular thread finishes. So basically what happens is there is say thread 0, thread 1, and thread 2. So because we create 3 of them, right? And let's say the time will be here, and when we do this start here, let's say we do a start here, this starts executing, but then we create the second one, we do a start for the second one here, and then we start the third one over here, and all the time actually this is running, right? This is running, and this is running, and after a while or we actually do this join here, we actually might be over here after starting this one. Let me write it over here. We write this join, but it might be that this process is not finished yet. So we actually will wait until this thread is finished. Let's say thread finishes here, and then this join stops, and we actually go here and we do a join here, but it might be that all of the threads take the same amount of time. So and as we started them sequentially, we probably have like this kind of same kind of time that it takes to start and join them. So all of them finish after we do the joins, and then we finish this 4 as well. This 4 will be finished, and all of the threads actually are running then in parallel. So as you can see, I will maybe then illustrate this a little bit more. Is that one color time, but it's one color time is a specific amount of time, but we are actually doing all of the colors in parallel. So we are actually finding all of them all together. Find them all in parallel. So this is how the multi-threading will improve the speed. Well, we can do a little quickly mention the other way. So if it's done sequentially, then we find blue, and this is also the time here. Then find red, and then find yellow. The proportions should be the same, so probably it takes the same amount of time to find each color. But basically, as you can see, the time that it is taken to completely find all of the colors will be 1, 2, and 3 times as much. So if we can use threading as we have done here, we will save basically 3 times as the time. And when we look at these the results here, it's, well, it is quite so it is basically 3 times faster, roughly. Yeah. So okay, but let's maybe look at the other ones also, just to maybe know. We also had this thread pool version. This thread pool and threading is a little bit different in terms of how you set it up, but the main part here is that we also have these masks that are put in a list, and then we create this using this with statement. We create this executor object, which is actually this thread pool executor class object, and you specify how many workers there are, and we have 3 workers, so 1 worker for each color, and then you specify what is each thread should do, and you submit to this executor this this method that you want to call. So it's kind of similar as it was in the threading. So you have mask and color you specify as arguments here, and then you, well, with the list comprehension, you actually create these all of these futures list, and then you do the same kind of thing that we had before. We had these thread joins. Well, we had this, let's say, yeah, well, thread 1, thread 0, thread 1 join, and so on. But this is almost the same, right? But you specify or write it down in a maybe more concise way, and it should have a little bit less overhead somehow. But when we look at the results, thread pool executor is over here, and it is actually, for our case, for my PC or my CPU, which is very, very old, like 8 years old or something. So it is for my configuration, and for this task it is lower. Okay. The next one actually was this region properties. So it is kind of the same as before, but this time what we do is actually we try to find these x min, x max, and y min, y max with a single call. So this scikit library will give this region props function, and you can get it from there with this. And yeah, it should make it a little bit faster, but when we look at this result here, it's not very much much faster. Yeah, and then we have another approach where we add to this props this threading, or not threading, or thread pool executor, which we discussed already, but we do this x, y, and or x and y minimum and maximum calculations done actually with this with using this region props. And one important thing is that it only works in these VBots because we don't have this ski scikit image installed on the robot, so it will not work there on the physical robot. Yep. So next one we had this site by label bounding box with number optimization, and it's almost the same as we had before, but this time this parallel is false, and so I just not cover it in depth. So we had this one over here, but this is very, very similar to the best one, so it's just a few milliseconds difference basically. Yep. And then we had site by label but with number parallel. So before we had this parallel was false, this time it is true, and rest of the stuff is the same. And what we saw is that it's again pretty much the same, almost the same as the fastest one we had, is threading. And for this particular case, it said actually that parallelization might not have been possible. It did not find anything to improve, and yeah, so this parallel equals true might not always give a better result than parallel equals false. So yeah, these are the imports over here. One maybe honorable mention in some sense is this multiprocessing. I have commented it out, which is actually one other optimization technique, but it's not possible to use this optimization technique in these VBots because this, as the name implies, when you do like parallelization with let's say threads, as I demonstrated, it creates threads which are like in like a this specific term or specific technique, but the other one is to create more processes. So you can have like a single process that is running with the main calculation, but when you want to do something in parallel, you can create more processes that will run, but we cannot use it in the VBots case because the VBots is connected. This specific robot.py that we are running is connected to VBots simulator, and it is connected actually this like one connection to one robot.py process. So if we try to parallelize using processes, all of the processes try to connect also to VBots, and it will not work. So it's just specific to this simulator case, but in practice or in other cases where you might want to parallelize or optimize, you might very well be able to do it with multiprocessing, and whether it is better or not depends on what exactly you are trying to optimize. So it's just you can try and see. One other technique for optimization that I will not cover, or it's very difficult to achieve again for the simulator case, but in general it is quite good, is using you can use PyPy. So this could give a huge boost, and because it compiles this code, and also it could give a huge boost, but it depends on a lot of factors again. So it might not give a big boost. So as we see that there are many different ways of making improvements, and if you ask say AI or ChatGPT or Claude or whatever, Gemini, then these AIs can say basically each of them might say that different method is the best, but it really depends on the case. So sometimes some method might be better than the other one, and therefore you should also try different methods and see and measure and see how well each technique performs. So that's basically it about optimization. Good luck.